Welcome to Academic Gurus Tutoring Thursday, where we answer all of your high school, college, and university questions. If you would like your question to be featured on next week's Tutoring Thursday, please submit your questions to questions@academicgurusinc.com. Don't forget to subscribe so you can stay current with all of our new videos. Today's question was posed by Dallas, and the question reads, Taipei 101 is sited in an area that is prone to earthquakes and typhoons, both of which can lead to dangerous oscillations of the building. To reduce the maximum amplitude, the building has a tuned mass damper, a 660,000 kilogram mass suspended from 42-meter-long cables that oscillates at the same natural frequency as the building. When the building sways, the pendulum swings, reaching an amplitude of 75 centimeters in strong winds or tremors. Damping the motion of the mass reduces the maximum amplitude of oscillation of the building. How fast is the pendulum moving when it passes through the equilibrium position?
Now, let's talk about the motion of the simple pendulum. So, what makes the pendulum swing back and forth? It's because of the restoring force, F. This is the component of the weight, mg, tangent to the motion path. So, F equal minus mg sine theta, with theta is the angle that the string makes with the vertical line. The minus sign here shows that the force is in the direction opposite to the angular displacement theta. The displacement x equal L theta. So, if theta is small, but how small it is? If theta less than 15 degrees, we can call the motion simple harmonic oscillation, and F can be approximated at minus mg theta and equal minus mg over L x. If we compare with the Hooke's law, which is F equal minus kx. We see the similarity here. So, the effective force constant K equal mg over L. The period T equal 2 pi square root of L over G. And the frequency equal 1 over T will be 1 over 2 pi square root of G over L. Next step, we consider the energies of the simple pendulum. First of all, I want to mention about the potential energies in form of 1/2 kx squared, when x is the amount of the movement from the equilibrium position, O here. The second energies I want to consider is the kinetic energies 1/2 mv squared. The total mechanical energies, which I call ME, is the sum of potential energies and kinetic energies, and this quantity should be conserved during the motion. So, when the pendulum reaches the highest position and stops, the kinetic energy is zero, and the potential energy is maximum. On the other hand, when it passes through the equilibrium point, O here, it has its maximum speed. It means the kinetic energy is maximum in that case, and the potential energy is zero. Before we start solving our problem, let me explain why we can consider the motion of the pendulum in our problem to be the simple harmonic oscillation. The first reason is that the mass of the pendulum is 660,000 kilograms. It's so heavy compared to the mass of the cable holding the pendulum. The second reason is that the length of the cable is 42 meters, compared with the amplitude only 75 centimeters. So in this case, A is really small compared with L. So that's why we can consider the motion of the pendulum is the simple harmonic oscillation. Okay, given the amplitude that I call A, we can find the maximum potential energy. That's equal 1/2 K A squared. And remember, K equal mg over L. As I said before, when the pendulum reaches the highest point, that is point B here, and it stops, it has 0 kinetic energies and maximum potential energies. And on the other hand, when it comes back to and past the equilibrium point O here, the potential energy is 0 and the kinetic energy is maximum. So in fact, all of the maximum potential energies at point B will transfer to the maximum kinetic energy at point 0 based on the conservation of energy. So at point 0 here, I can write out the kinetic energies at point 0 will be equal the potential energies at point B. Now the kinetic energies is equal 1/2 mv squared. And the potential energies at point B, it gets the maximum potential energy. So we can use the formula 1/2 mg over L A squared. As you see, m here can be cancelled. So actually the velocity at point 0 that I call v squared will not depend on the mass of the pendulum. That would be equal g over L A squared, or v equal square root of g over L A. The final step is plug in the number. We are given the g, the gravitational acceleration, 9.8 meters over second squared. The length of the cable L equals 42 meters and the amplitude 75 centimeters. Remember to change it to meter. So we plug in the number, we calculate it, and we got V equal 0.36 meter over second.
Thank you for tuning into our Tutoring Thursday channel. If you enjoyed watching this video and found it helpful, please give us a thumbs up, comment, and subscribe. We would love to hear from you. Until next week's Tutoring Thursday, happy studying.